Mr. Chairman and colleagues, thank you very much for this opportunity of presenting at the Society of Vacuum Coaters conference. I'll be talking about manufacturing thin coatings by thermal spray methods. I'll be leading you through a story that starts off at technical readiness level number 2 that goes to technical readiness level number 8. My name is Chris Berndt and I'm the Director of Surface Engineering for Advanced Materials at Swinburne University in Melbourne, Australia. Before we get too far, I'd like to dedicate this talk to our heroes. These are the healthcare staff and essential service personnel who have demonstrated their commitment and self-sacrifice throughout 2020 and beyond. Thank you very much to our heroes. Surface engineering for advanced materials is a highly desirable activity. I'll be leading you through a story which first of all addresses why thin is highly desirable for technological applications. I'll be addressing why we use thermal spray and how we actually carry out this process. It is important in point number 3 to address what the customer wants. Of course there is risk, and then I'll be talking about who do we really work for and talking about the future. First of all, we should look at and compare coating processes. And I've just outlined several in this sheet. I'm talking about thermal spray and physical vapor deposition. And these have a variety of characteristics, 1 to 9 and many others, ranging from operating costs to the materials that you can use. I've just highlighted 2 of these, one in the blue box and one in the orange type box. So coating thicknesses, for example, for thermal spray range from 10 micrometers to centimeters, while PVD is typically in the order of 1 to 20 micrometers. Likewise, the surface finish for thermal spray coatings is coarse, whereas for PVD it is smooth to high gloss. And there are other coating technologies such as plating, chemical vapor deposition, hard facing, additive manufacturing, and there are many versions of additive manufacturing. The point of this slide is to indicate that there are many attributes for various coating processes, and depending on what the customer wants, a selection is made of these processes. I'll be addressing thermal spray by liquid thermal spray techniques, but in the back of my mind, I will always be comparing them to PVD and other atomistic techniques. So first of all, let's look at a typical microstructure of thermal spray coating. On the left-hand side, we have a coating. This is bronze of 90 copper, 10 aluminium. You see the roughened substrate. Sometimes you may see grit entrainment. You see the lamellar type structure with cracks, unmelted particles, pores, and we define these microstructural units as splats. And here's another example without all of the numbers and arrows on the actual micrograph. So the defect features of these coatings are composite-like. We have oxides, porosity, lamellar boundaries, rough surfaces, and chemical profiles. These coatings are really ugly when you look at them. But keep in mind that they're being used at technical readiness levels of 8 to 9. So although they may be considered as being quite strange or ugly, they do have beauty. And the beauty is contained within the defective features, which I'll describe in more detail. So thermal spray processing integrates science and engineering. So we have powder injection, inflow phenomena, and impact with the substrate. We have a diagram of a plasma torch, and in the process of thermal spraying, there will be air engulfment. The particles which go into the plasma effluent by particle injection may oxidize, and then at some point, usually about 6 inches or 15 centimeters from entry, these individual particles will splat and form saucer-shaped deposits against the roughened substrate. So there are many aspects within this process which require control. Otherwise, the quality will be quite severe. So the 3 major ones which I've picked out here would be feedstock quality, the spray parameters, and the surface prep. So in this introductory part of my talk, I'm going to describe how the process zone impacts and affects the coating quality. And if we can change this process zone, then we can actually change the coating quality and the attributes so that the performance can be enhanced. So here's a nice image from Professor Vardel in Limoges, France. And what you can see from this real image are all of these micrometeorites called particles, about 1 million per second, coming down onto the substrate, and in some cases they rebound. And the impact of many millions of these will, over time, build up an integral coating. Throughout this talk, I'll be giving various references from the literature that goes back many years. So, for example, here is some work of splat impacts of stainless steel particles by Professor Huben in the Netherlands in 1988. His experimental work was translated into schematics that very clearly showed that depending on the Thermospray process conditions, these singular splats either had very smooth features, as shown by my pointer, or in certain conditions, they gave rise to a large number of cracks. So one of the major points is that the Thermospray process conditions gives rise to different microstructural features. Another work from Stony Brook University in New York also looked at singular splats. And here we have a single splat, and that has been interrogated by various image analysis techniques so that either radial cracks or circumferential cracks could be well defined. And the addition of these two crack networks gives rise to the ultimate properties of the whole structure. So processing cracks were induced and could be relieved by heat treatment, and then loading cracks form under surface conditions. So the defect taxonomy depends on the degree of melting, and some of the key work was carried out by J. Majewski in 1976, and more recent work by Ang et al. What this cartoon demonstrates is that there are many features within a coating. So we have the substrate, we have a bond coat, and then we have a splat structure of a ceramic overlay. And with the various colour renditions, we're able to see inclusions, oxide splats, partially melted particles and unmelted particles. And together, the composite of all of these defects gives rise to the ultimate properties. The point that I'm getting to is that if we can control these features, and if we can control the splat size, then we can change the nature of the coating and become very competitive with physical vapor deposited coatings. So we have a toolbox. We have a toolbox and a palette of micro features. So we have a structure. The microstructural artifact could be over-blasted areas, embedded grit blasted, coating roughness, unmelted particles, giving rise to all of these artifacts. And we include porosity, vertical cracks, horizontal cracks. We have a process, so we have the impact of the processing tool, which could be grit blasting, the feedstock size, the thermal spray parameters, the standoff distance, and other factors. And then finally, we have the property. The structure and the process influence the property, adhesion strength, low roughness and poor adhesion, variable physical properties, micro-hardness properties. All of these material properties eventually give rise to the functionality of the overall coating, hence applications and the commercial incentives. So we have a palette and we have a toolbox, and that gives rise to applications. So more sophisticated work on splat morphology looks at individual splats. Here is a real splat is actually a high entropy alloy in this case, magnesium, cobalt, chromium, iron and nickel. And we have a splat which appears to be partially melted. And we have the splatter marks of impact against fragmentation against this small surface. That is related to high temperature processing and the impact momentum. And you can also reveal these splat morphologies by carrying out 3D profiles under optical sensing devices. Here you see a splat which is raised above other splats underneath, and you can see splats being formed and being revealed across the surface which is being sprayed. So let us go back to our table of contents and address some of these specific questions. Why is thin highly desirable? Thin is highly desirable because it is advantageous to form nanostructured materials. However, individual nanoparticles cannot be thermal sprayed due to their low mass. And what this very simple diagram indicates that because of their low inertia and their low momentum, they would essentially just bounce off the thermal spray process zone. And they segregate in the stream periphery without depositing onto the substrate. Note that conventional thermal spray particles are of the order of 10 to 100 micrometers in diameter. We get around this issue by a technique which is called liquid thermal spray. And in about 1997, this was at the technical readiness level of about 3 to 4. And this shows you the setup that we're talking about. So we have a liquid feeder shown in red, essentially a perfusion pump that feeds a liquid and particles into a spray torch. These particles enter the spray flame, and they can either be collected by electrostatic precipitation or they can carry on unimpeded to impact against the substrate. This work was carried out by Conductivity et al. So the precursor solution is atomized and injected into the flame. Now we have nano-sized particles that are formed by flame droplet interactions, and the green tick indicates that the particles can be collected as a particle or as a powder, or as a deposit. The actual system talks about the specialized liquid injection arrangement. So it is very tough just to feed a liquid into a flame. So what we do is that we have a hypodermic syringe needle feeding the liquid under pressure. We have an atomizing gas so that at the exit of the liquid injection port, we have atomization of the liquid, and then we get these very fine particles being formed. So the liquid thermal spray provides microstructural features of a thin film, but, and this is a big but, the bulk features of a thick coating. So we're getting the features of both thick and thin being formed simultaneously. An important note here is that I'm using the term liquid thermal spray. That includes two techniques, one which is called suspension plasma spray, SPS, and the other technique which is called solution precursor plasma spray, SPPS. And again, there is a seminal paper by Conductivity et al. In 1997. So the model for the ultrafine particle synthesis process is as follows. We have liquid droplets that enter the flame, the liquid evaporates, the solid phase of precursor condenses. This is the stage A. In stage B, chemical reaction can begin, grains can nucleate and grow because they're so small, they're nanostructured, recall. Chemical reaction occurs, sintering occurs, dense particles can form, and then in part C, these aggregates can be formed, large particles can be formed, or agglomerates. So the point now is that we're able to go from a liquid being injected into a flame to some result, some particles being formed that can then be deposited against the substrate. So let me provide an interim summary. Just like the Starship Enterprise, we are all explorers. To date, I've addressed technical readiness levels of 2 and 3. I've described how the processing conditions are very critical for thermal spray, and they become even more critical for liquid thermal spray methods. The control of the process is imprecise, and the coatings so formed are defective, but that does not necessarily mean that they are poor coatings. So now I'm going to see how we can transition from the technology and science into engineering applications. We're going to talk about some of the customers who can take advantage of this technology and progress towards TRL levels of 7 and 8. I point out that the microstructures of these coatings are in fact very beautiful. So future manufacturing technologies include thin films, thick films, and layered or near-net shaping. Thin films have functional nano features and thick films have protective functional coatings. And they can address various segments ranging from bio, electronic applications to traditional aerospace, mining, power generation. And this all depends on the materials engineering of the microstructure, from nano to meso to macro. So for thin films, we have functional nano features, and for thick films, we have protective functional coatings. And all of these can be wrapped up and controlled by Industrial 4.0 in robotics, artificial intelligence for remanufacturing and repair. So liquid thermal spray provides the best of both worlds. First of all, the microstructural features are those of a thin film, whereas the bulk features are of a thick coating, as you see in number 1 here. So by liquid thermal spraying, we've got both thin and thick film attributes. So we have the nano features and the protective coating as shown in point number 2. Here's an important note. I'm using the term liquid thermal spray to include both suspension plasma spray, SPS, and solution precursor plasma spray, SPPS. I'm going to go through several case histories now where liquid thermal spray has been used to advantage. The first one comes from some work by Gerl in 2018, some 20 years after that original work by Carthaginian. And what we see here is a SPPS, a liquid thermal sprayed YAG coating, yttrium aluminum garnet. And look at the microstructure compared to that of a conventional atmospheric plasma sprayed ytterostabilized zirconia coating. What you're able to see is a very fine structure with vertical cracks compared to lamellar cracks in the conventional coating. So straight away, we see that there is a different functionality within the liquid thermal sprayed YAG coating. We still have an ytterostabilized zirconia interlayer, the bond coat sprayed onto the superalloy. When we look at the thermal conductivity of these coatings, we see that those of the SPPS YAG, the liquid thermal sprayed YAG, are much better than those of the ytterostabilized zirconia coating. So we have a thermal conductivity of 31% compared to something like 60% for the original APS coating, atmospheric plasma sprayed coating. And to quote the paper, by introducing unique engineered microstructures generated using the liquid thermal spray process, it has been demonstrated that an existing material can meet and exceed all of the major performance standards of the current state-of-the-art coating. So there is good news with regards to case study number 2. Case study number 1. Case study number 2 really addresses a TRL level of about 4 to 5, where we are literally combining solutions, metal alkoxide solutions, with various chelating agents of PVA, citric acid, oxalic acid, forming sols and gels, and these are sprayed directly into a plasma torch. This is groundbreaking work by Sanpo et al. In about 2013. Now, the purpose of this work was to look at the splats which are so formed, and then by analysing the splats, come to an understanding about the degree of melting and how an integral coating is built up. So this work demonstrated that the solution precursor plasma spray technique could produce cobalt ferrite splats. The importance of this work was focused towards antibacterial studies, and the whole thesis, the latter chapters of the thesis talked about the antibacterial properties of these liquid thermal sprayed coatings. Case study number 3 comes from Scandinavia. And again, they were using liquid techniques, liquid thermal spray techniques, and by changing the process conditions from these 4 micrographs, you're able to see that the microstructure was vastly different, with either vertical cracks, interpass porosity bands, branching cracks, to porous coatings which seem to be reasonably homogeneous with regards to porosity, to intercolumnar cracks, very similar to those which can be produced by physical vapor deposition. So to quote from that paper, the techniques, the liquid thermal spray techniques, offered significant advantages for generating nanostructured coatings, better control of the coating chemistry, and microstructural features. So there is a lot of evidence as well from this work that the thermal conductivity also was very low, where a low thermal conductivity is much preferred. The higher porosity links to lower thermal properties for the solution, for the suspension plasma sprayed thermal barrier coatings. The role of column density, intercolumnar spacing on the thermal properties was quite complex, and there was no evidence that large intercolumnar spacing played a significant role. So there is a lot of evidence that these coatings have great functionality. A more recent review by A.S.M et al., this came out just a few weeks ago in the Journal of Thermospray Technology, looked at the microstructures of suspension feedstock fed into a high-velocity oxygen fuel torch, suspension feedstock compared to conventional feedstock. The micrometer marks are approximately the same, but you're able to see that the suspension feedstock gave rise to a much finer microstructure where you can actually see some of the carbide particles, whereas are very obvious with regards to the JP5000 and the jet coat high velocity oxygen fuel processes. So the HVOF process reduces the thermal loading on particles but increases the particle velocity, and the suspension high velocity oxygen fuel coatings are very dense, the lamellar structure quite fine, a uniform distribution of these particles, and after post-heat treatment, they could be crystallised to form amorphous and nanocrystalline phases. However, and this is a big however, there was still decarburization. So this work can be followed from that of A.S.M et al. And a very nice review concerning solution techniques is picked up by Fauché in this issue of the Journal of Thermospray Technology in 2008. So let us address some of these questions quite clearly. Why is thin highly desirable? Because the microstructure has a good performance. We use thermal spray under atmospheric conditions, so this implies, or this means that we're not using any vacuum at all, and we're using LTS, liquid feedstock methods. So the customer, as we always know, is quite demanding. They want no surprises. They want a reliable coating and low-cost solutions, affordable at a TRL of 7 to 9. So they essentially want a structure and a process that gives rise to a property with high functionality, a lot of applications at low cost. So getting to the 2 final questions. The risk. The risk is how do we navigate the valley of death, and what are the future applications that will progress liquid thermal spray methods. So let us go back to this slide that addresses the processing of coatings. We have inputs, powder injection, in-flight behaviour, impact with the substrate, as indicated by this picture. And we have variables, feedstock quality, spray parameters, and surface preparation. To get to technical readiness level 5, we need to understand these effects for liquid techniques. The liquid viscosity, flow rates, chemical speciation, process temperature and velocity effects, roughness effects, suspension versus solution methods, post-treatments, and many other factors. These factors are pointed out by Girl in 2018, as well as by Fauché in a review paper in 2008. So there are many variables during any thermal spray process, and I don't really intend to go through all of these variables, but just lead you through the physical setup, thermal spray process, particle parameters, spray conditions, transient properties, feedstock properties, substrate conditions, splat formation, coating formation, applications, and the various industries. What liquid thermal spray promises is to jump the valley of death that goes from points 2 to 6. So we have a physical setup that can go directly to applications and the various industries that we wish to approach. So here are some of the future industries. The coatings that I'm showing you now are produced under conventional atmospheric plasma spray conditions with conventional feedstock. They are ceramic biomaterials that show the typical splats with cracks, pores, splats, unmelted particles, a material called Berndt-Additive, and the conventional hydroxyapatite. The physician, the orthopedic surgeons that use these coatings would really like thin coatings rather than thick coatings. Rather than having a coating which is 100 or so micrometers thick, they would love to have a coating which is integral and fully dense at a thickness of, say, 10 or 20 micrometers. So there is a compelling technical need to manufacture thinner bioceramic coatings with a design porosity that allows bone ingrowth. So let's try to summarize all of these features. We've got a vision for innovation called liquid thermal spray. We have a toolkit called the thermal spray torch with a special injector that allows liquids to be injected into the process zone. We have a microstructural palette composed of many defects and splats. These defects are not bad. They can be used to advantage to have certain functionalities. These building blocks are grown by using the LTS technique for various targeted applications. We can use thermal spray by liquid techniques in combination with atmospheric techniques, and Girl showed that in a slide about 5 slides back. But then we have future applications such as microelectronics, bioengineering, energy harvesting for photovoltaics, sensors, and many other applications that will be grown if we can have thin coatings produced under atmospheric conditions. I'd also like to dedicate this talk to many of the past thermal sprayers who have impacted my life directly, and some of these sprayers have departed, but I'd also like to commend the future generations, and these are some of the people at Swinburne University who will be the future thermal sprayers and carrying the torch. Finally, I'd like to acknowledge that this work has been supported by the Australian Research Council in a training centre called Surface Engineering for Advanced Materials. And I'll leave you this final slide again as a summary slide to indicate that these beautiful microstructures are no longer ugly ducklings, but swans that will attack many new innovative areas of technology and performance. Thank you very much for your time.